perpendicular lines, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular lines, angles sharp as ice, maths and physics, yeah, the future's real nice.
Boom, 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 boom. All right, what's up, everybody? Got our chat working. Yes. Here's my chat. Here's my chat. Cool.
Oh, yeah.
Happy Monday. Today is the start of my last week of teaching at UCLA this summer.
That's dope.
I'm so happy. This summer has been a lot more stress than I wanted it to be. So I will be mucho happy. I mean, the teaching's been fun. I enjoy the teaching. It's just all like the headaches of grading stuff not working and administration things. I had like an idea of, if universities keep spending all this money to hire admins and things, why don't we just have those admin people deal with all the admin stuff? Like, what if a professor just like never had to answer an email? Like, never had to deal with a student saying that like my cat got diarrhea, or like, can I get an extension on this? Be like, you got to go talk to administration. Don't talk to the professor. Because I swear, I love the teaching part of teaching. Teaching is great. It's all the babysitting that I don't like. And it's only getting worse. I think it's because parents are becoming harder, and it's becoming harder and harder for parents to actually parent because they have to go work like 3 jobs or something just to like stay afloat. So that kind of gets like shoved to the wayside. I don't know. That or like social media. It's like a lot of stuff going on. What's up, Taco? Good to see you. Pinhead said, I'm taking Calc 3 next semester. Am I going to die? No. You're not going to die. I will say, I think Calc 3 for me was harder than Diffie Q, but I really like Diffie Q. Calc 3 is not going to kill you, though. What's up, Fembox? What's up, Ansh? How's it going?
Hello, Professor. I'm good. How about you?
I'm good. It's Monday. I'm as good as I can be on a Monday.
Yes.
Oh. Bonjour. Ew, French. All right, let's see. Let me check Campus Wire. Do you have any specific questions, Ansh, you want me to go over?
Oh, yeah, I was hoping if you could go over like some of the questions on the exam I got wrong.
I can totally do that, yeah. Which ones do you want me to do?
Oh, the first one would be question 8.
I can do all of them. All right, let me do question 8, yeah. You're good. All right, exam 2, question 8. Oh, is this the one with the... No, that coax was question 4. Yes, here we go. The energy stored. Yeah, there we go. Okay, cool. This was a very... I think I did this one during office hours. I didn't do the energy stored, but I did do the, like, what's the overall, like, capacitance.
Yeah, this was really similar to that one question from the homework.
Yes. Ooh, oh, I did add another capacitor, though, it looks like. I think I added this one as well.
Yeah, I think that was a factor.
Or this one. Yeah. So it... Oh, sorry. You can't see my screen, sorry. Yeah, so I think before... Like, this capacitor wasn't there, for sure. Oh, okay. I did make this one tricky.
Oh no.
Okay, but it's very similar. It's very similar to the other one. All right, so let's see. And they all have different capacitance values. So you're not going to be able to make the symmetry argument that we did last time. Although, were you here when, I think it was Emily and I were, like, bashing through one of these?
Yeah, I was there when, like, the thing about, like, how if one of them is different, then the middle one doesn't cancel out, I think.
Yeah, but then we were going over... Yeah, it didn't cancel out, right? And we actually could figure out the voltages. Yeah, that's
yeah.
pretty cool. Should I buy a dino blade? What's a dino blade? Is that the Sawzall thing, Breasticles? Is that what people are using to, like, cut down these cameras I keep seeing about? Oh, it's a game. Never mind. Okay, I was thinking about something else. Don't come after me, Palantir. That's a game on Steam. Cool. Games on Steam are fun. Okay. Dude, what are you doing, Microsoft Copilot? Chill. All right, so these two are definitely in parallel with each other, right? We understand that? I see that for sure, right?
Yeah.
Good. Perfect. And luckily they're the same, actually. That's pretty cool. Okay, C4. C4. All right. I think with A, what like made things a little tricky is I put another resistor in series before going to the things in parallel. So you're going to have this. So C1. And then we have our parallel action here. So I got this going to C2, and I got this going to C2. Okay, cool. So, let's put it up. Okay, this is C2. This is C2. All right, let's figure out how the other stuff's going. So this end of C4 is connecting to C2, but it's also connecting to something else. Okay, so this one still connects to C2, so we can do this. And then C4, this one also connects to C2. I'll use a different color. Dinosaurs fighting with swords? I mean, it sounds kind of dope. Okay. I think I see what's happening. And then now C3, right, is in between these two. Do you see that? So C3 actually does this. Okay, here's the key thing. There still is symmetry here. Do you see how on this leg I have C2, C4? And on this leg, I have C2 and C4.
Yeah.
So I actually, I can ignore C3 now.
Okay, yeah, that's what I assumed during. This is the exact like setup I had during.
Oh, perfect. Okay. All right, so then let's see what went wrong. Okay, so I have these two capacitors in series. These two capacitors in series. So if we look at, let's say, for instance, this together. Let's call that like C24. For capacitors in series, I know that's going to be 1 over C2 plus 1 over C4. all to the minus 1. Okay. And then that's going to be the same thing for this. This will also be like C24. Okay. So now I have C1 here. And then I have C24 here and C24 here, right?
Yeah.
Good so far? Yep. Okay. So now let's take these and I don't know, I'm going to call that like C2424. And that's just going to be C24 plus C24. So it's really just going to be 2C24. Okay. So then now this is in parallel with this. Sorry, in series. And so then C1 24 24 is equal to 1 over C1 plus 1 over C24 24 all to the minus 1. Okay?
Yes.
Okay, you got that far, yeah?
Yeah.
All right, so then if you want energy, so I mean plug in numbers, right? So you have different numbers for what all these things are?
I think, yeah,
Yours
they are
pretty-
different.
How different are they? What were your numbers?
Mine are 3, 0.426, 1.02, and 3.1.
Right, so 3 point what?
Oh, 3.1. Oh, sorry, just 3 for the first one.
3, yep.
And then 0.426.
Okay,
And then 1.02.
okay.
And then 3.1.
Okay, let me check. I want to check something real quick. This is question 8, right?
Yeah.
Let me see. I want to see what the ranges were on these things. Okay, question 8. Okay. Okay. All right, that makes sense. Cool. And then sorry, let me make sure that's what Kudu recorded as your things for your let me see. Last name. No, go back. This is 104. Wait a minute. Wait. Oh wait, that's not question 8, I don't think. It's question 7. Okay, 1 sec. There we go. Okay, 3.06. Yes. Wait. Okay, yeah, then what was your voltage? When it said the voltage between the points here?
It said 3.06.
Okay, good. Okay. All right, so that's working correctly. I'm curious. I'm guessing you're gonna ask about questions 9 and 10 as well, right?
Oh, yeah.
Perfect. Yeah, when we do those, I really want to see what's going on because Kudu's just off its rocker, dude. For whatever reason, on questions 9 and 10, dude, nothing matches up at all, and I'm so like, what the fuck is going on?
Like after submitting the exam?
Well, did the numbers change for you after submitting? Did they look like they changed like last time?
This time I haven't noticed anything
Good.
yet. Like I don't remember if anything changed.
Well, yeah. I feel like I'd get a lot more people saying that they did if it did, but so I think I fixed temporarily the issue of them having it change before and after the exam. But as I'll see when we do questions 9 and question 10, the issue is that whatever they have for like their grading thing is still not working. It's still like doing weird shit. Okay. We'll figure it out.
Yeah, it doesn't seem like it's changed so far.
Okay, good. Okay. Well, I'm happy about that. So I got them to fix one thing at least. I was like, I really need this to not break on the final. That's awful. Okay, let's see. Let's plug some numbers in, yeah? To see if we get like the same capacitance, right?
Yes, please, because I don't know if maybe I messed up something on that.
It's okay. You know, I'm here. We'll try it out. Okay, what's up, Justin?
Yeah.
Justin, you want to play some Red Sack later? I might have some time. All right, so I'm gonna do everything. I'm just gonna leave everything and do microfarads at the end. I feel like. Okay, so 1 over 1.66 plus 1 over C4, which is 3.03, and then we're gonna do that all to the -1. So that's 1.07 is what I got for this.
Should ours be the same, like, regardless of like the individual capacitances? Like, is it intended to be?
Oh, you're so right. I didn't use your numbers. I'm so dumb. Sorry, I copied mine and not yours. Thank you.
All good.
No. Yes, we will eventually have to convert to farads. You're right. Thank you, Famish. I do need to drink water. Okay, so let me fix this. So then this was 1.02. And this is 3.1. Alright, let's try this again. Water is good. Water's great. Alright, C2, so 1 divided by 0.426, right? Alright, let's see. Nice, Justin. Yeah, get it on console. Get that aim help. What do we call it? Aim assist. Okay, that and then to the -1. Okay, so I got 0.37. Is that close to what you got?
Yes.
Perfect. 0.37. I'm gonna say 375 microfarads. Okay, so then this is that times 2. Not too hard, right? That's 0.749.
Yes.
Great. All right, then let's do here. So your C1 was 3. So I'm going to do 1 over 3 plus 1 over this thing. All the -1. I'm going to get 0.599.
Yeah, I got that too.
Oh, perfect. Okay. So then they wanted the energy stored. So that's just 1/2 CV squared. Right? So that should be 1/2 times 0.599, and then just times voltage, which in your case was 3.06.
Oh, I missed a 1/2 because
Oh, okay. It's fine.
like what? Oh, sorry. Continue.
No, you're good. Say what's up. What's up?
Oh, no, I realized what I did was I did Q total equals to C times V, and then I did U equals to QV, so basically like CV squared. And
Sure.
so I don't have a 1/2, so I think that's why
Oh, okay.
because I thought it would be like the potential energy. So that would potential energy would be U equals to QV, right?
Interesting. Charge times voltage. Yeah, that's for like an arrangement of charges. That's a totally different.
Oh,
Yeah, Q times V. That's the energy. That's the electric potential energy of an arrangement of charges.
so 1/2 CV squared is for capacitors.
Uh huh.
Oh, okay, I understand. Thank you.
It's all good. I guess I could have led with that. I could have led with like, "Hey, what was your final thing you did?" But okay, it's okay. This is still good to go through this. And then that would be microjoules, because the capacitance was in microfarads. Which, yeah. Yeah, Kudu at least says that was the correct answer. Wow, good job, Kudu. You did something right today. Love it. Dun, 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 dun. Okay, all good. Just a little slight misunderstanding about like electric potential energy. Yeah. So the other key thing we want to know: do you know how to figure out like the energy stored in like a network of like resistors and stuff?
Could you go over it actually?
Sure. So this is energy in a capacitor. For resistors, we say like the electrical potential energy. That's just equal to current times voltage.
Okay.
So if you know the current going through a resistor and you know the voltage across the resistor, that's the energy that's in the resistor. Well, actually, really, it's the power, I guess, technically. Sorry, it's power. There's similar concepts. Power is like the rate at which energy is being dissipated. But those are like two things they'll usually ask. They'll ask like, what's the power draw of this series of resistors? Or they'll ask like, what's the potential energy of the series of capacitors?
Okay.
Cool. All right.
Yes,
You want help with 9?
yes, please.
All right, let's do it. Okay, what numbers did you have for this? Now I'm curious.
For alpha, I had 5.02.
Uh-huh.
For R1, 0.157.
Uh-huh.
For R2, 0.507.
Okay.
And then lambda was 3 to the times 10 to the negative third.
Perfect. So, yeah, those are the right numbers that I think you should have had. Kudu said your alpha was 7. Your R1 was like 0.2. I'm like, no.
Come on, man.
Yeah, it's screwed up. It's screwed up, dude. It's screwed up. It's screwed up. It's okay. I'll figure it out. Or I will figure it out. I have to figure it out because grades are due in like 2 weeks. It's just annoying. All right, but let's do this question. Grading be damned. Knowledge and science and physics is the most important thing. Okay. Consider an infinite length shell which contains a non-uniform volume charge density. Rho is alpha over r. Okay. So that's what the volume charge density is here. In the center is an infinite line charge, which has a linear charge density of this. Okay. So this has a linear charge density. This is a volume charge density. So key thing here. So Q is equal to either like rho dV. Or this is what we'll call like dQ technically. So this is for volumes. Or it's equal to lambda dL. And then this is for like linear charge densities. And then you could also have this sigma dA. And then this is for like surface area charge densities. So it's like 3 different dimensions of charge densities. You can have it be a linear density, where if I multiply by a length, then I get how much charge is there. You can have it as a surface area charge density. So if I multiply by the area, then I get the total charge. Or you can have it as a volume charge density, where if I multiply by the volume, then I get the amount of charge that's there. Those are the 3 different types. And I put 2 different ones on this question. I gave you a volume one, and I gave you a linear one. Okay. What is the question actually asking? What is the total charge? Oh, this is great. I know they said per unit length, okay? So really what they want Q total, which is going to equal like Q, they want charge per unit length, so Q over L. So that's equal to, that's equal to Q tot over L. Okay. So, of the non-conducting shell. So that's this. Okay, cool. So let me figure out what Q tot would be, right, for this. And that's this type of shape. Okay, so I'm trying to find, and it's also, there's kind of there's a hollow part to it, right? What's up, Monkey Man? All right. Okay. So I want to think about, how do I figure out how much volume is here? Right? There's going to be some volume amount dV. So some amount of this dV that I'm going to multiply by my volume charge density. And then that's going to get me the amount of total charge that is there. If this volume charge density was constant, so if it didn't depend on any variable, if it was just like a constant amount, then all you would need to do is just find what the volume of this whole thing is, which that's just what is that? It's just pi r squared inner, pi r squared outer times the length. Do you understand, Ansh, how you would find the volume of like this region?
Yeah.
Right.
So like, yeah, like the density times the volume.
Is the total charge. So if rho was constant, so if rho didn't depend on r or anything, then Q tot would just be equal to pi, and then we'd say like r2 squared minus r1 squared, and then we would say like times L. Do you understand why this is?
Yes, because it's
Right.
like uniform, so you could just multiply it by the
Volume, right?
whole
Which
thing.
is, if I'm trying to find that, right? It's the whole circle minus the small circle, and then times the length, right? To get volume.
Yes.
Good. Okay. Now the issue is I can't do that because rho is not constant. Rho is a function of alpha. So we're gonna say, but rho is equal to alpha times 1 over r. So it depends on r. So what I need to do, it's similar to what you've done in calculus. Have you ever done like volumes of revolution? Long time ago, probably, right?
I think so.
Okay. So what I'm going to do is I'm going to think about a thin sheet that is like the sidewalls of a cylinder. So yeah, let's describe like what dV here is going to be. So dV is going to be equal to like the surface area of like a cylindrical sidewall, and then times the thickness of that like cylindrical sidewall, which is going to have a thickness of dr, and then we're going to say like times the thickness. Or I don't know, if you want to get like weird, it's technically the girth. That's technically the term.
You done messed up, Aaron!
That's fucking sus, but yeah, it's technically what it's called. And so this is dr, and then this is going to be 4 pi r squared. This is the shell method in calculus. Again, why this course is technically calculus based. Does that make sense?
Sorry, I don't know why I'm confused on the 4 pi r squared.
Yeah, actually, yeah, it's not 4 pi r squared.
Oh, okay. Oh, yeah, that's
Sorry, it's 2 pi r l. Dude, I don't know. Thank you. Yes, sorry, I'm getting ahead of myself because I'm thinking about the spheres. The spheres is 4 pi r squared. That's the shell method for spheres.
And
Does
also,
this-
I wanted to like. Oh, sorry,
Yeah.
go ahead.
No, you go ahead. What's up?
I was wanting to like clarify like why it is 2 pi RL.
Sure. So
Oh,
let's think about like a cylinder, right? How do you make a cylinder?
a rectangular
piece of paper.
sheet like rolled up.
Perfect. Yeah, rectangular sheet, right? Yeah, you take a rectangular sheet, and then you wrap it around, right?
Yeah.
Okay. So if I were to unwrap this, that would look something like this, right?
Yes.
Where this dimension of the rectangle, right? This dimension would be this. And then
Right.
this dimension, right, would be this.
Oh, so the circumference 2 pi r is one length,
Perfect.
and then the L is.
Yes.
Yep.
Yes.
That's
This
cool.
is 2 pi r, and then this is L. And then, of course, right, this is on its side, technically. So that's why, like, 2 pi r times L.
That's cool.
Cool. I'm glad you asked about it. Okay, and so, yeah, so that's the area of, like, a side, of like a little sidewall. And then, so what I'm going to keep doing is I'm going to make those, like, bigger and bigger. And so I'm going to expand it out by some amount dr, and that's how I get a volume. Do you see how if I do like this times this, that gets me a surface area, and then if my sheet was, for instance, like a height dr, then I would have a volume. Because then this would kind of like extend out this way, like dr, and that would give me a rectangle. A rectangular prism. So 2 pi RL. That gets me the surface area. And then dr gets me like the height of that sheet, which when I wrap around gives me a volume, right? It's not just a flat sheet. It's a sheet that like has like a little bit of like thickness to it, and that creates a volume.
That makes sense.
That makes sense? Okay, cool. Yes. So what I'm gonna do now for my integral, right? So I want to get what Q total is, right? So Q total is always the integral of dq, which in this case is going to be the integral of rho dv. And then for a cylinder that we're coming out this way, that's going to be equal to the integral from r1 to r2, right? This is my starting radius and my final radius. And then it's going to be rho 2 pi r L dr. So the bounds here, right? Tell me like what size cylinder to start, and then R2 tells me like where to stop. Does that make sense?
Yeah, like grabbing the outer shell.
Yes. Good. Okay. And then remember that rho was equal to alpha over r, I think, right? Yeah. So this actually makes your integral actually kind of nice. Right? Because this was alpha over r. So now when you integrate that, the r's are going to cancel.
Emotional, damn it!
Bye-bye. And then this is r1, r2. Cool. And so then now you just have 2 pi alpha integral from r1 to r2. And then that's equal to r1 to r2 dr. And so that's just going to be 2 pi alpha r2 minus r1. Oh, and don't forget there's an L, okay? There we go. And I know my alphas always look like CX's, so I need to get better at doing alphas. There we go. Femvox says, you should work out how many hours you've done on office hours since you started streaming. It's a lot. I've calculated it. It's a couple thousand, I think. I'll look it up for you in a bit, Femvox. Okay, so this is Q-tote, right?
Yes.
But then I want charge per unit length, so I want Q-tote over L. So do you see how that then just becomes all of this divided by L?
Oh.
And then so then this is your
I
answer.
thought it was the R2 minus R1. That's what they meant by the length.
Ooh, yeah, no. That's the radius.
Yeah.
Was this the answer in the solutions? Actually, I should pull the solutions. Sorry. Yeah, this was question 9. Yeah, perfect.
I think I didn't understand the 2 pi RL well. That's why I messed up on this problem. Because
Yeah.
I used pi r squared instead.
I think I saw someone was commenting about should I use the pi r squareds? I'm like, wait, what are you guys doing with pi r squareds? That's the end cap. And I think we said this thing was infinitely long or something. Yeah, it's an infinite line charge. So the end caps, they exist all the way out at infinity. They don't really contribute anything. Yeah.
So is it possible I could get partial credit on that?
Oh yeah, yeah, you'll definitely get some partial credit for sure. Yeah. And then if you want more partial credit, there's always the regrade thing. You can always just tell me hey man, I got close. I know some professors that just give 0 points for that. I think that's awful. It's so demoralizing. 0 points. I tell them as long as you do something physics related, I'll give you at least half. Okay, cool. All right, so that's that question. Or that's part A. How many parts did I have this? Jesus fucking Christ. Wait, what? There's a part F to this? Oh dear. Oh dear. I did put a lot of parts in this. Okay. Okay. Calculate the magnetic field when R is equal to 2.6. So So that's like way far out, right? Okay. So this one is just the standard. You should know this. The standard equation for the electric field due to an infinite line of charge. Do you know what the equation for that one is?
If I'm not wrong, is it lambda over 2 pi r epsilon naught?
Yeah. Yeah, I think it's like 2k lambda over r, which also works out to be that as well. Yeah. So lambda. Okay, yeah. So Frenchman says there's more parts. Uh-oh. There's a lot of parts in this one. Okay, the electric field, right, is equal to lambda. And also, this is lambda enclosed, by the way. Over 2 pi epsilon naught. R, right?
Yeah.
Okay, cool. Right. So, in that case, the lambda enclosed, well, you're going to have some amount of positive charge enclosed here, and then you're also going to have charge enclosed in here. Luckily, we figured out what this was, right? We figured out lambda of the shell. Lambda is always charge per unit length. That was equal to this. So that's going to be 2 pi alpha R2 minus R1. And then plus lambda, because there's also an inner conductor that also has charge on it per unit length. And then that's all over 2 pi epsilon naught r. The reason this is similar to like the sphere thing, whenever you're looking at whatever electric fields are outside of symmetric things, you can always take these and like compress them down into like a single thing at the center. So when you're doing, for instance, like the electric field of a sphere, and let's say you're doing it out here, you're looking at, hey, what's the electric field out here? You can treat this whole thing as a single point charge of whatever this total charge is, and this also as a single point charge of whatever charge it is right there at the center. You're allowed to like compress them down.
Wait, sorry. So sorry, could you like repeat it?
Yeah, for sure. Okay, so in the case of anything that's like symmetric meaning by, well, that's not symmetric. Squares are not symmetric. Circles are symmetric. Okay. Okay, so let's say, for instance, if you had a sphere, right, of a certain radius, let's say radius r, let's say r1.
Yeah.
And you're looking at, hey, what's the electric field out here? You're like, what is the electric field? Yeah?
Yes.
You can condense this thing down to be a single point charge located at the center.
Oh, right.
Right? I can't draw right now, but there you go. So this is the same thing as a single little point charge there, and then you're measuring this as your R. You don't care that there's charge out. You don't care that there's charge in between the center and the outside of the shape.
Right.
So it's the same thing here for the cylinders. So I know technically, like, this cylinder is at the center. That makes sense. This cylinder is like a shell, right? It has hollow space in the middle. But because I'm trying to figure out the electric field outside of it, I can like basically shrink this whole thing down into another like equivalent single line of charge.
Yeah,
that makes sense? Okay. Yeah, okay.
So
that's,
and since
yeah.
the length sorry.
No, go on. You're good.
Since the length cancels out, like, that's why it's just It's just like a point charge as well.
Not because the length cancels out. So sorry. So when you're doing, so this is again the equation for like an infinite line of charge. But notice how for an infinite line of charge, you're not doing like Q tote. You're not doing Q enclosed. You're doing lambda enclosed, where lambda is equal to the total charge of the line divided by the length. And that's what we calculated here in part A. We calculated effectively what lambda of the shell was, because we calculated the total charge on the shell, which was this, with the length. And then when I divide by L, now I get lambda of the shell.
Okay.
And what that's a fancy word for, right, is that I have a linear charge density now, so that if I multiply this by L, see if I multiply this by L, I get the total charge. So that's all we've done. We've converted our shape, or we've reduced our shape into a very simple thing that if I just multiply by the length, I get the total charge that's there. And then when finding the electric field due to a line of charge, I don't need the length of it. I just need the lambda.
Okay.
Okay. All right.
So we're using lambda.
Mhm.
We could use Q total as well, but like if we rearrange like lambda.
Yes. So, okay, this goes back to like, just for like, here, let me write it somewhere else. So for an infinite line of charge, do you remember the Gauss's law derivation of this?
Yeah, it was the E times dA, the integral of E dA equals to Q enclosed over
Perfect.
epsilon.
Right, so E dot dA was equal to Q enclosed over epsilon naught. The charge enclosed, that's equal to lambda times L. All right. And then dA, for a cylinder, that's equal to 2 pi RL. Right? That's the area of the sidewalls. Okay. Do you see how the length cancels out?
Yes.
That's why you end up getting that E is equal to lambda over 2 pi epsilon naught R. Yeah.
Yeah.
So for infinite lines of charge, I don't need Q enclosed, I need lambda enclosed. Which is,
That makes sense.
again, yeah, that's why in part A I had you go find lambda, because part B requires you to have it, because this is lambda of the shell, and then this is lambda of the inner conductor. Okay.
Yes.
Okay. So then part C asked for what do they want? They want the magnitude of the electric field when R is equal to 0.4. Where's 0.4? Oh, so 0.4 is like in between somewhere. Oh, okay. So they want the electric field when you're in between R1 and R2. Because R1 was 0.1 and R2 was 0.5. Yeah. So this is, R is in between R1 and R2. Okay. Again, this one is a little painful.
Would it be that the electric field, like of the inner thing, is still like the same, but then we have to like integrate for the?
Exactly. Yeah. So for the inner thing, right? So you have E times 2 pi R L, basically, right? is equal to Q enclosed over epsilon naught. Now for Q enclosed, that's going to equal positive lambda times L, right? Because that's what this is enclosed. But then I need this amount that's enclosed. I need the amount in between R1 and R2, yeah?
Yeah.
So then that's where you do, okay, well that's plus the integral from R1 to R, right? I don't, whatever, in this case it would be 0.4. And then that would be the 2 pi RL rho dr, which I guess is 2 pi RL lambda over R dr. And this is the same thing we did up here. To figure out, we did it from R1 to R2 to get the total charge from R1 to R2. Here I want the R enclosed. Sorry, I want the charge enclosed at some magic value R, some mystery value R, I guess, that's in between R1 and R2. So instead of having this go from R1 to R2, we just have it go from R1 to R. Does that make sense?
Yes.
Okay. Cool. All right. So yeah, you can do this integral, right? This cancels, which is nice. And so Q enclosed. So Q enclosed is just equal to, we're gonna say L times, and then this would be lambda plus 2 pi alpha R minus R1. And then when you divide by this, right? So E times 2 pi RL is equal to this. Well, now I can divide by L. Oh, sorry, and this was all over epsilon naught, right? And so I get that E is equal to 1 over 2 pi epsilon naught. And then this is going to be, I'd say, lambda over R. And then you can say plus 2 pi alpha minus 2 pi alpha R1 over R. So if I pull the R in, this is this divides by R. This cancels out the R. And then this is R1 over R.
Yeah, that makes sense.
Okay.
Thank you.
Oh, I see. Dude, yeah, wait, what? Why did all the question parts get duplicated?
Emotional damage.
Oh, I'm seeing this shit you guys were talking about.
Yeah, it's sorry.
The fuck? When did it do that?
It's not on my end right now. I just logged in.
I see it, dude.
Yeah, I don't know why it's like that.
Ugh. So mad. So mad.
Obviously, don't
So
go
mad.
do that.
You do whatever
So
you
mad.
want.
We can't condone anything of the sort.
No, we can't live. Live.
Why? Why is it doing that?
Okay. Could I ask since we're on question 9, can I ask
What's
a few
up?
questions?
Of course, dude,
I'll
what's
admit,
up?
question 9 was the one I struggled with the most.
I know, you were messaging me a lot. It's okay. he
Yeah,
was
hold on,
like,
give me a second.
how do I do this? How do I do this? I think it was in the textbook, though. I'm pretty sure they did this. Or maybe not. Okay. Thank you, Hamster Bing Chilling. Yes, I do math and physics for fun. Yes. Well, yes. I'm technically getting paid for this, but I do a lot of this for fun.
I had to deal something real quick.
Alright, you're good.
As I was saying, right? Wait, can you guys hear me?
I can hear you. Yeah, what's up?
Okay. So on question 9, part A, I
Yes.
initially, so everything was like smooth sailing for the first like 5 minutes as I just like wrote stuff down and I had like
Mm-hmm.
looked at my diagram and stuff. So I knew off the bat that I had to find the total charge first to find the unit length.
Yes.
And so it already gave me that unit length, I believe, right? It's like 3 times 10 negative 3, something like that, right? Or-
Okay, yeah.
Or yeah, no, it gave me. I wanted to find the unit length, and it had like some infinite length L, so it gave me that, right? I had a variable.
That's
So
fine.
So what I started doing was like, okay, total charge. I was like, this is a non-constant charge density or whatever it is, charge volume density, I guess. So
Mhm.
I did the Q equals integral of P times dV. The first part I
Good.
struggled was like, hold on, dV, in my notes, I had it as like 9 times out of 10, it's the surface area.
Yes.
So I started with like the surface area equation using the one on the equation sheet, which was like 2 pi r L, then like plus 2 pi r squared.
Right. That's the end caps.
That's the end caps. And I did that for a while.
Yeah.
I had to do this little calculus that was a real pain in the ass until I realized as I got to the end, I couldn't factor out L.
Yeah, because the other thing doesn't have an L in it. The 2
So
pi r squared
that's-
doesn't have an L.
That led to me prompting you about, hey, can I do this thing where I just
Yeah.
don't disregard the end caps? And your answer is like, maybe, maybe not. I was like, you know what, good enough for me. So I just kept rolling with it. So then I did a thing where I started putting all my numbers in, and I was like, okay, radius 1, radius 2. I accidentally, I don't know why I did this. I think I was just tired and hungry, because I was in a different time zone when I was doing this.
Sure.
I accidentally added in R1, like an extra R1 to my equation, which was
Mhm.
basically double counting. But then as I was doing, I was like, okay, wait, hold on. And I literally go back and look at all these calculus problems. I'm like, this looks wrong.
I see.
So
Yeah. It
then
starts
I
looking like
fixed
too
it.
messy.
Yeah, but over this took me a while. So my work was kind of messy.
Mm-hmm.
But this whole time, so I thought R1 and R2, the numbers you gave, like to use for my mounds, was fine as is.
Sure.
I kind of just disregarded that radius of the charge line
Okay.
because I was like, oh, that must be for something else. Because I don't know. On my computer, the diagram was small. So unless you did like a 200 times zoom,
You were telling me that. Yeah. Well, especially on the what was it? The other one, the capacitor diagram. Yeah.
that and also like the one with all like the charges and like the squares and the circles and
So
all that.
You know this trick though, right? That if things look kind of
Yeah.
small, you just say open image new tab and then
Yeah, I know that, but I did it on this one. I didn't actually do it on this one until
I feel like you can see things pretty well here, no? So they were all asking me, they're like, wait a minute. I think it was this one, right? You guys were all like bugging because the 2 here is like not as faded as the Q, and you're like, wait a minute, is this like on the surface or not?
I was just going through Campus Wire because that one kept coming up, and I would have not have noticed that if someone at the bottom said, "Oh yeah, that's why there's."
I'm not gonna be
3
that
Q
tricky. I'm not gonna be that tricky. Yeah, I was like,
And I was like,
no,
oh,
it's
shit,
not half
is
in,
there-
half out.
So, yeah, until someone said there was 4Q and B in like Campus Wire or whatever, I
Yes.
was like, wait, what? So that's So I got So long story short, number A is wrong because my
This also, I
balance
feel like
was
I get that this diagram is like kind of a bitch to look at, honestly.
This diagram was confusing because you gave me like a like a density or like a permittivity or a resistivity or something for one of the jacket when it doesn't use the jacket.
Exactly. Yeah, that's the red herring.
I was
Because
so confused.
you don't care about the jacket because you're just doing the potential between the braid and the conductor.
Yeah. Like I went to your office hours beforehand, so like on I just had it pulled up like that coaxial cable thing and just like do from outer diameter to inner diameter, whatever the dielectric is. I'm like, okay.
Yeah.
So yeah, that was messing with me for a bit. But it was a multiple choice one, so I was just like, you know what, this looks right.
Yeah, you get somewhere close enough.
So I think based on for A, I know I got that one wrong, and I think that's why I got B wrong. Because my arc the charge value was wrong. Can I say what you were doing for part C?
Yes. Let me get to it. See, hamster Bing chilling. I'm a senior in high school. I'm trying to pursue engineering. Any tips which UCs to apply to? UCLA is the best.
I mean, wait, are you an in-state or out-of-state student? Because I'm from Texas, so I can
I'm from
tell
Texas
you
too. Wait, I didn't know you were from Texas, dude.
Where are you from?
That's
Texas?
cool.
Hold on, pause.
Pause.
Let me guess. Okay.
He wants to guess where.
I
where in
think you're
Texas I'm
either from Austin, San Antonio. Actually, no, wait, hold on. I go the other way. Are you a Spurs fan?
I'm not a Spurs fan, no. So I can't be from San Antonio.
Then, did you grow up? Actually, who do you support? Texas Tech, University of Texas at Austin.
UT, of course. That was my alma mater. UTA was University of Texas at Austin. That was my undergrad.
Okay. Then, are you from? You don't seem like a Dallas person.
No, fuck Dallas, dude.
Okay, well,
Absolutely hate Dallas.
ouch. I'm from Fort Worth, so.
Oh, it's okay. You're not from Dallas.
Okay, so are you
Fort
from
Worth is
Austin?
okay. Fort Worth is chill. I'm from Houston.
Okay, I was gonna say the last pick is Houston, or you're like from like Plano.
Yeah.
Or Waco.
I think there's another person in my chat. His name is Breasticles. He's a very smart guy. He's down at I think it's Corpus or something. Breasticles, are you
Corpus Christi.
Yeah.
Is he at A&M Corpus Christi?
I forget. He said some. The real question is, you're a diehard Cowboys fan for no reason, even though they've done piss poor yet. Dude, the Cowboys suck, dude. It's so bad.
Yeah, I don't.
Hey, Corpus. It's
Where
okay.
were you when they traded away Luka Doncic?
Oh, Luka Doncic. Yeah.
I
That's a
was
good
still in
question.
high school when
I
that
love Luka
hit,
Doncic.
and dude, the morning that news broke, everyone was mourning.
You got traded to the Lakers, right? Is that what happened?
Yeah, he got traded for the Lakers for the.
And he
equivalent
found out
of,
about it
like-
on the TV or something. He was just like, wait, I just got
and
traded.
He got traded away for the equivalent of like 2 sacks of potatoes and like 1 broken knee.
Oh no.
It's insane. Like the
Oh,
trade was
no.
so bad. Whoever the opposite end, like the trade,
Yeah.
when the Lakers accepted it, they didn't
Yeah,
think
the
it was
Lakers.
real.
Yeah, like this is a troll, dude. Absolutely got to be a troll. And now
Yeah,
he's crushing it
that's-
at the Lakers, though. I think he's doing pretty well with the Lakers.
Yeah, no, him and Bronny are so. LeBron
It's-
is so happy.
Yeah.
They added
'Cause-
5 years to that man's career
Yeah,
just
Bron-
by having another guy to play with.
Yeah. That's too funny.
Yeah,
oh,
but
we could go on for about football and stuff, and yeah. But one sec, let me answer the chat real quick for this kid. Yeah. I agree, Hamster Bang, with Jack's analysis here of like, yeah, if you're in state or out of state, it makes a huge difference because out of state tuition to UC is expansive.
it sucks. it's
Absolutely terrible.
it's actually like I think it defeats the purpose of going to a public school versus
Correct.
a private school.
Correct. Absolutely. 100%.
Like the only reason, so the other place I was considering when I was a senior, I'll admit, when I was a senior, I was a tryhard and applied to all these schools
Sure.
that I
Some
had
reach
like,
schools.
I got into some reach schools. This
Oh,
is the
good for
crazy
you.
part.
Oh,
So
nice.
like I had lined up, I could have gone to Purdue, I could have transferred it to UT Austin.
Uh-huh.
I could have potentially even gotten into Michigan if I didn't like rescind my wait list, right?
Sure.
And I even at one point was like waitlisted at Cornell, but like I was like, I'm not getting into
Dude,
Cornell.
Cornell sucks though, dude. It's upstate
Cornell
New York,
is-
dude. No one wants to go to upstate New York.
Ithaca is a very sad place. I will.
It's a
admit.
very sad, dude. They've installed like nets to prevent people from like committing suicide. Like they
Yeah,
have
that
nets
doesn't
on the
surprise
bridges. Like stop jumping, please.
Yeah. And like of course I also got into UCLA, and I also
Nice.
got into Colorado School of Mines.
Oh, that's another
Uh,
good engineering school.
It's a
Those
very
are all really
engineering
good.
school.
Yeah, Purdue's a really good. I actually just went to my friend's wedding. He did his PhD at Purdue, and he works for NASA now. He's an aerospace engineer.
Yeah, no, Purdue is an awesome school.
Yeah, it's a
And I
great
mean,
engineering school.
For reference, the reason why I chose UCLA was
Yeah, why
one,
did you?
UCLA got back to me before Purdue did. I
Uh-huh.
initially got waitlisted at Purdue, but the first day they started taking people off the waitlist, they let
Okay.
me in.
Okay.
So by then I already kind of had a recency bias because I visited UCLA in the interim.
And Los Angeles is great, dude. The weather is so much better than middle of fucking nowhere, Indiana.
I mean, okay, I spend most of my days in like Missouri, so I'm not
Oh,
used
okay.
to nice places.
You're not used to nice places.
No, I shouldn't say that, but I'm used to sitting in cornfields and trees. Like I've seen.
There
that
you go.
stuff.
You're used to
It's not like-
concrete and yeah, got you.
It's not like they're gonna break me, but yeah. So like the reason why I chose, so I guess like the last my final 4, I guess you could say, were UT Austin. One because it's cheaper, but they had
Yeah.
a thing where it's like because I was a private school kid, I didn't get automatically admitted. Because it was
Oh, the top 10, the top 10 rule. I think
Yeah.
it's like top 3 now. They keep
It's
dropping
they
it.
had to shrink it because just they let so many kids in.
Yeah, exactly. Yeah.
So if I wanted to get in, I had to spend a year at a UT Austin, not Austin, Arlington. and then have to fight to transfer back in.
Yeah, the other
Not even for my
UTA.
guaranteed major. And I wasn't. This was also during the time where like higher education was having a stroke. Let's just put it that way.
Yeah,
And
Trump was cutting funding left and right.
that too, and it was like also like record number of kids.
Sure.
Like my class of 2025, we broke every scale on like how many kids applied.
Oh, interesting.
Yeah, because like I think like even at my school we had a small grade, but like me and a few other people, I went to a Catholic school.
Sure.
Like we had like 6 or 7 kids get into Notre Dame.
Yeah,
Which
it's a big Catholic university.
Notre Dame's a great school.
Yeah.
But it's like it's crazy. Like you had so many kids going into school at one time that it was kind of like, hey, this time next year, are they going to honor these agreements? Is the goalpost going to change, kind of thing?
Right.
So
I
that's
see.
what
So,
was one thing.
so UCLA gave it to you, and you're like, this is guaranteed. Let me just take it.
UCLA would give me my major up front, which was huge.
That's dope. We like that.
And so my other options were Purdue and Colorado School of Mines.
Uh-huh.
Purdue was cheapest, and I really, really wanted to go Purdue for a whole year. But ultimately, Purdue was like, we won't give you your first choice of major. I'm sure the guy, what is his name, Breasticles, whatever.
Breasticles.
He's at. I'm sure he's heard about the infamous first-year engineering program at Texas A&M College Station.
Yeah.
I don't know if you've ever heard of it, but it's basic. I'm sure you've heard of A&M, right?
Oh yeah, of course. My sister went to A&M.
Oh yeah,
One
you're
of them
from
did.
Texas. What am I thinking?
Yeah.
Sorry.
Yeah. You're okay.
But like the first year engineering program, I have so many of my friends in it, and it sucks because
Oh no.
guess how big their first year engineering program is.
I don't know. Probably 2,000 or something. 3,000.
You can guess in the thousands.
4,000. 5. I don't know. How many thousands are in engineering? There's like 50,000 total, I think, in school. Can't have like more than 10% being engineering. Bum bum. Jack, did we lose you? We lost Jack for a second. Let me see one sec. Hamster, you're in-state, great. Electrical engineering or mechanical engineering, which one's worth it after graduating? I think those are both pretty valuable, honestly. Depends what you like more, honestly. If you like electronics and circuits and stuff, which is what I really like to do, I honestly would have gone electrical engineering. My major I ended up doing my PhD in physics, but physics is basically, at least plasma physics, what I did, was basically adjacent to electrical engineering. And so if I had to pick one of the engineerings, I probably would have done electrical. I will say it is very, it's very technical in terms of like, I don't know, having to know all the circuit stuff and all like the signal analysis. There's probably some Fourier stuff in there too, right, Breasticles? So electrical engineering is probably the toughest, I would say, out of all the engineerings. Mechanical is probably the widest breadth of other things you can go do. So mechanical engineering, you can go into like manufacturing bridges or I guess that's civil engineering, but like cars, whatever, anything that needs to get built, mechie will probably do it. So it's more hands-on. Mechie is definitely a more hands-on if you like building cars and those types of things. Double E is you're going to be sitting with like a multimeter and a soldering gun and doing all sorts of stuff. Double E is for Chads. Yeah, okay.
Yeah.
And Mechie's also difficult? Yeah, probably. So yeah, I think those are both great majors. And honestly, if you wanted to do them at UCLA, they're both great programs at UCLA. And that's where I teach, if you wanted to come by. I teach physics there. But any of the other UCs are really good with engineering. I want to say UCI is pretty good for engineering. And then, there he is, Jack's back. We had another student who went to Cal Poly SLO for aerospace engineering. Apparently they have a really good aerospace engineering program at SLO.
Yeah, sorry, my Wi-Fi crashed.
Oh, you're good, dude.
But yeah, as I was saying,
thousands of people at A&M, right? For engineering is what you're saying?
Yeah, the first year engineering program, this is just like people taking it for their first year, maybe their second year ever.
Mm-hmm.
The total number of people there when I was applying was 12,000.
Jesus!
Not
12K?
That's not in their engineering program as a whole. That's just freshmen.
That's just
like
freshman engineering.
Sophomores retaking it.
Wow.
So, and they only end up taking about 3,000 kids out of that to the next stage.
Oh,
So-
interesting. They cut people out after the first year.
It's more of like, so okay.
I know
if
people
you
like
make it
fail
through your
out.
first year.
People fail
Yeah,
out for sure. I understand that, but
Yeah,
I didn't know if
people
they were
fail out
like
for sure.
actively cutting people out.
I mean, they do kind of cut people out because so after your first year in the first year engineering program, right?
Yeah.
If you have made it to the end, which a lot of people do not make it to the end, they
Oh, no.
they try to cut people out. You have to then make an application to get what kind of major you want.
Gotcha.
Some students get priority versus others depending on how you do with your application, etc. Right?
Okay.
There's no guarantee if you are like a mechanical engineer or an aerospace engineer. Good luck.
I
It
see.
is incredibly sought after.
Yeah.
So they
Okay.
only take 3,000 people out of whoever starts that year.
Wow.
So that's why you have so many people who come back again to retake it.
Yeah, I'm just trying to get in. I see it.
Yeah, so that's why it's not a great deal. I know a lot of people who had to go through it, and they made that
Breaks them.
it was needlessly difficult on themselves.
Sure. That's the other thing. Like you have to balance, giving yourself a challenge and also still enjoying yourself because it's a very unique time in your life from being like 18 to 21. You don't want that to be just like pain and sitting in a room crying all the time. Like you want to grow up at least and like have a happy time. Somewhat, please.
I don't know. I feel like when you go to college, you got to work hard. So yeah.
I agree. Work hard, yeah, 100%. But also like leave some time and space to develop like friendships and like social interactions because it's a very rare time. College, just trust me. Like afterwards, that never happens again in your life. So try to leave. Like you can join like cool clubs. Like I was a part of like the robotics club at UT. I was a part of physics club. I was part of these like all these related to my major clubs, but they still had like social things that I went to. So I wasn't always like stuck in my room like doing homework. So I mean, adjust.
Yeah, that's real. And then so that's why I didn't go to A&M. But my the two I was like really close to considering, like I almost went to there, was UCLA and Colorado School of Mines. Colorado School of Mines is an amazing school.
Yeah.
I don't think you can go wrong going there.
Yeah, is that in Boulder? Or I'm thinking CU Boulder.
No. Colorado School of Mines is up in like Colorado, kind of like Springs area, I think.
Oh,
like,
I love Colorado Springs. It's a great place.
It's actually, I don't think it's in Colorado Springs. It's somewhere around that. But
It's in
it's a
Golden.
small school, like 7,000 kids.
It's in Golden.
It's basically yeah, it's in Golden, Colorado.
Oh, I love
And
Golden.
the place you're thinking of, Boulder, that's University of Colorado Boulder.
Yeah, that's another good school.
I also got in there, but they were also having like this like weird, you gotta be like this sort of like major to get what you want. And we gotta put you on like this like, I don't know, it was a whole thing, but I didn't want to go there. So yeah.
Everything happens for a reason. You're at the school doing your thing,
Yeah,
you choose
I mean,
the path.
I feel like once you go to college, you're gonna realize, hey man, in high school, making you sit in a desk for 8 hours a day, it was crazy work.
Yeah, having like eight classes and keeping up with all that shit. I don't know how the fuck we did that in high school. I'm like, excuse me.
I think you did it because you had a whole year and not 10 weeks, but that's
True. That is true.
And
That is true.
if you played your cards right, were 3 of those classes really real classes? That's kind of what I did. But I think the reason why I chose UCLA over Mines, one, I did like a decision matrix, which helped a lot.
Ooh,
It really
okay.
helped to
Did
get
some
your thoughts on
analysis.
paper.
Yeah.
It's also like once I went to both places, I asked, okay, I can see myself living here in both places.
Mm-hmm.
But being in LA has respectfully just afforded me so many opportunities.
Yes.
Like it's insane.
Everyone's
Because
here.
I'm not even talking like, oh, I live in LA and I can go to the Kia Forum. I'm talking like, whoa, hold on. Every couple weeks, big companies are coming out here, local companies like recruit kids. I joined I joined a racing club. Just one weekend, we got to go learn how to like weld by going to like the small business who we were affiliated with.
Oh, dope.
And like
Dude, I
even
want
like
to learn how to weld.
besides that, what else did I think? Yeah, it was just like a hey, come learn. We want to teach people kind of thing.
Yeah, you also got to consider
yeah,
that when
so,
going to a
like, I would
college. It's like
say
what
go down.
opportunities are there as well. LA has almost everything.
Yeah, like that's the problem with like Mines and Boulder. Well, they definitely had a network of like jobs and stuff. Like they had a career center like we do. It was also that if you really wanted to like do something like big in industry or whatever, you had Denver, and that was like obviously it's a big center. I'm not downplaying Mines at all. I have so many friends who are going there who graduated the year after me. Like I know you're in good hands. But I mainly chose it because LA, and also I think I just like having like a bigger school. Like UCLA outside of engineering is a better school than Mines. If you like look at other stats, I don't think that's like an offense to people. Like look at our like I don't know, look at our math, look at our physics, look at our
We got Terrence
science,
Tao.
look at our
We got
like,
T-Tao, baby. Got Terrence Tao.
Yeah, like and at the time it's also like my sister went to Berkeley.
Oh, okay.
So like she also was like, hey, UCLA is a good school.
Yeah.
Go.
It's better than Berkeley.
So yeah.
Screw Cal. I'll have some.
Yeah,
hate for
Cal
Berkeley.
Bears you.
Yeah. Also, like,
But
ew,
yeah, so
Berkeley?
that's ultimately why I choose it. I just feel like once you're like 6 months into it and you've really like started to build your college experience, I guess. You're like,
your routines.
okay, I made a good move. I'm on to bigger and better things. Obviously, look before you leap, because some people I know like Florida State University to basically have spring break every day, and I was like, that's cool for you. But yeah.
Yeah, you can't major in beer pong, unfortunately. They don't give you jobs for it.
That's right.
All right. Did you guys have any other
So, I
questions
mean, yeah.
about these parts?
Oh yeah,
Just to-
actually,
just to
sorry,
make
I
sure.
got off the.
You're okay.
tangent.
It's okay.
Back
It's cool.
to my
It's cool.
questions.
Yeah, back to what your actual questions were.
For question 9, part C.
Yep.
Can I see what you did for that one?
Yep.
Okay, so I think.
So standard Gauss's
Yeah,
law.
I think I was.
Eat.
Yeah, standard Gauss's law. 2 pi theta. Yeah. Okay. R. Yeah. I see what I did there. I think I just messed up parts A, B, and C because my original value for A, my answer was wrong.
Sure.
So, would you say, like, all my work seems to be correct? Would you say how many points is that?
If all your work's correct and just like part A was wrong, I don't know, maybe like 25 out of 30, 23 out of 30 or something. I'd have to see what like part B and part C were. I have to see if you did like the integrals correctly there as well.
Oh wait, integrals for part B and part C.
Well, part C has another integral, so part C has this integral you got to set up.
Oh, I didn't integral. Oh, see, what I did was
because you still have to do it out
just-
to R. You have to do it out to R, or did you do it as like a percentage of R1 and R2? I guess you could have done.
So
that.
what I did was
No, it's not linear, though.
I basically just stole the end result of my total charge.
Yes.
That I used in part A, and I just threw that onto part C, and I just changed what R1 and R2 were.
Oh, okay. Okay.
So, just to save me time. Well, I thought I could do that.
No, you can. You totally can do that. I mean, you leave R1 and then R2 just becomes R, but then you still have to do the integral. Right? In this case, the integral is like super basic because the R's cancel out.
Yeah, my integral came, so I didn't do the integral on part C, I did the integral on part A, and just took whatever the equation was for total charge. Like after I'd integrated it and threw it into part C.
Yeah.
But then I just changed R1 to R1 and then R2 to the 0.4.
Oh, okay, yeah. Yeah, that's fine.
Then
That's
I got
legit.
some number times the factor L.
Yeah.
And then I just added it with my given total charge for that little line charge thing. Not total charge, but charge density. And then I just kind of like factored out stuff.
Yeah.
So I guess you could say I jumped around a lot. That's definitely what you could say. Because at this point, I was just trying to save time.
Yeah, I know. It was a lot of time, this question, especially if this was actually 6 parts. I'm glad it was only 3. I saw the 6-parters. I'm like, oh no.
Okay. Then for parts A, B, and C. So part C for number 10. I mean.
Okay, let me go to part 10. Ansh, did you have questions about 10 as well? Just so I know like how much of 10 you want me to
if
do.
you could please go over that.
Yeah, let me just roll through 10. Let me just roll through 10, and then
Sure.
we can ask along the way if things don't make sense. Okay, there we go. All right. All right. Question 10 was okay. A non-conducting solid sphere is inside. Oh, I made them both non-conducting. Okay.
Mhm.
A solid spherical shell. The dimensions are shown below. Blah blah blah. Cool. I'm gonna leave everything as variables, and then we'll whatever you just plug things in at the end. Okay. Did they have? Oh, but they at least had standard charge densities. I didn't put any trickery here on this one.
I think you did. Yeah.
I did. Yeah. They're at least just they're normal. It's plus Q and minus Q for total charge, and I said it was uniformly distributed. Yeah. Yeah. Good. This last question, the reason why this one was tricky is because the charge density was not uniform. This one they are. All right. So at 2.5a, you're going to be here, right? Somewhere in between.
Yeah.
And so Q enclosed. Sorry, let me get a little bit less of a font here. So Q enclosed is equal to Q, so positive Q inside, and then plus the fraction of minus Q. And so that's going to be 4/3 pi r cubed over 4/3 pi. Oh, I remember what I have to do here. So this is actually a pain in the ass. Okay, fine. All right. One sec. So I'm going to say like volume percent times minus Q. So it's the percentage of volume enclosed going out to 2.5. Okay. So percent volume is equal to like part over whole. So that's going to be 4/3 pi, and then we're going to say r cubed minus r1 cubed. So that's like this minus this. That gets me this amount. And then the total is, or the whole is 4/3 pi, and then this is r2 cubed minus r1 cubed. Does that make sense to everyone? Where that came from? I can explain the geometry if it doesn't.
Okay, yeah, I see it, yeah. Because that's the volume, right?
Yes. Yeah, so 4/3 pi r cubed is the volume of a sphere, but we have like, in order to create a shell, it's like having a big sphere minus a small sphere. And then we have like this in-between sphere. So we're doing like the in-between one minus this one to get this volume, and then the total volume is this one minus this one. So then E times 4 pi r squared is equal to Q over epsilon naught minus, and then this is going to be Q r cubed minus r1 cubed all over epsilon naught r2 cubed minus r1 cubed. And then you got to divide by this. So it's actually quite ugly. Yeah. So 1 over 4 pi epsilon naught. And that's going to be Q over r squared. And then minus all this over r squared. And just whatever, just put another r squared there. I think that's what we had. Yeah, oh, and they put the numbers in as well. Okay, that's fine. Yes. Okay. So in this case, I guess you could simplify it, right? Because R is equal to 2.5a, R1 is equal to 2a, and R2 is equal to 3a. So what would that be? E 1 over 4 pi epsilon naught. This would be q over 2.5 squared, and then minus q 2.5 cubed minus 2 cubed. I'm just taking all the a's out because well, actually, did I tell you what a was? Oh, I did tell you a, sorry. So this is going to be 1 over a squared. Yeah, okay. And then that's over 2.5 cubed, 3 cubed minus 2 cubed. Yeah. The other way that they do it in the solution is they figure out they figure out the volume charge density, and then they just figure out the volume that's enclosed. That works as well.
Yeah.
But these should give you the same as here.
Yeah, I did not even do it remotely close that way. Okay. So what
What
I
did you
did
do?
was, so I tried to find the, well, first I did the integral of, sorry, give me a sec. The integral of the electric field times dA equals charge enclosed over permittivity. And I got the dA equals 4 pi r squared. And I basically worked out my equation to have electric field equals K over Q enclosed over 2.5a squared. That's what I had for that.
Oh, okay. Yes, that's for the first one, right? Yeah, okay, sure.
Yeah. So where I kind of messed up was then I tried calculating the enclosed charge. So what I did was I had the total of charge, I guess positive Q, that little circle in it.
Uh-huh.
And then I had to solve for the partial charge of, I guess, minus QB.
Yes.
Then I was like, oh, okay, it's kind of similar to last question. So what I do was I get an integral, and I'm like, okay, the partial charge of the negative Q that I want to find equals the integral from 2a to 2.5a.
Okay.
Then I'm like, okay, then it's
That's
times
okay.
PR times dV. And I'm like, well,
Yes.
PR, it's a constant. So I'm
Yes.
like, I can just say this is 1 or whatever and just drag it out or whatever.
Okay. Yes.
And then it was like, okay, then I just need to find dV. And I'm like, dV is the
Yeah, what is dV for a sphere?
oh shit.
Should be
I
4
put-
pi r squared dr.
That's where I messed up.
And I think you'll notice something here. Look what happens when you do this integral here, Jack. Do you see how you literally just get 4/3 pi r cubed?
Yeah, I think I may have jumped a step and I put in the integral 4 over 3 pi r cubed.
Oh, so now you're integrating superspheres or
So-
something.
I definitely think I may have made a calculus mistake.
Yeah.
That's on me. So what I do was, okay, so then I integrate that and I get, I move my constant out. So now I have 4/3 pi. The constant, let's say 1. We're getting rid of the.
No,
we're
you
just
have
setting-
you have to define this though. You have to define what rho is. Rho can't just be 1.
Yeah, I should have realized that. I still set it to 1 on my paper, so that's my fault.
So rho in this case would be minus q, and then it would be divided by the volume, right? And so that's minus q, and I would say over 4/3 pi, and this is where you would say like 3a cubed minus 2a cubed. Because then that right here,
I did not
that's
get
the
that.
volume of this. Yeah.
Yeah, I did not do that, so that's my fault. So then after that, I work it out more. So by now my solution's kind of off because now I have now I'm integrating in R-fourths.
Yeah.
So it snowballs from there. So what I ended up getting,
keeps going down.
was a completely wrong partial charge of the negative Q.
Yeah.
So my total charge enclosed is off,
Correct. Yeah.
and that's why my final solution's wrong.
And I'm guessing part B and part
So-
C will also be wrong from that too.
See, okay, that's the one thing I wanted to ask. So for part C, right, on question 10,
Yeah.
whenever I looked at this question, I was like, hold on, this is a conductor question or a capacitor question.
Uh-huh.
And so then I was like, I looked at my equation sheet, my little equation sheet, and on it I had the equation for what is the find the electrical potential difference. And I have it somewhere. But basically on my equation sheet, it told me how do I find the
Oh, we
capacitance of
did
a
this. I think I did
capacitor
this with you during office hours, right? The capacitance between.
vacuum.
Yeah, I think we did do this.
I don't know if it was me, but I had it from the equation sheet, so it's like, oh, okay, this is easy. And I just threw the numbers in. And I was like, I think this is right. And the weird thing was, I remember checking Kudu,
Mhm.
like the first 20 minutes after the exam closed, and it gave us solutions.
Yeah.
It said my answer was correct, and that was 6.69 times 10 to the 11 power farads.
Okay.
But then I come back a day later and check it, and it's like, no, the answer is 0. I'm like, what?
Disqualified.
Wait, what? God damn it, Kudu.
Like, no shit. I was like, did I hallucinate this? But, I remember, then I looked down, I'm like, no, I was right.
Yeah, so Kudu wasn't supposed. So that's actually the fact that you were able to see solutions right after the exam closed. I forgot to set it to not release that until a day after, because there's always some student who's like, oh man, I was 30 minutes late. Here it is. And so I realized it probably 10 or 20 minutes in. I was like, oh shit, I shouldn't post the solutions right after the exam closes. So then I re-switched it to have them post after a day. So
okay, then.
But now I'm curious. It showed it as being correct the first time, and then it showed it as being incorrect.
Sure. I'm positive it says 6.
So I mean
because it says my answer 6.69 e times the negative 11, and then it said correct answer 6.69 e to negative 11.
So that tells me that maybe me changing the setting there re-triggered something.
Because right now it says correct answer is 0 farads. Right now, as I'm looking at it on Kudu.
Okay, let me look at it.
If it just showed me the wrong answer before, I wouldn't sweat about it. But I think did it show me the right answer?
This is why, again, don't trust anything Kudu says. As long as you put things on your sheet, I'll figure it out eventually.
Okay.
It wasn't supposed to be like this. It's not like this, but okay. Let me actually look. Let me see. All right. So you put in yes. I see. Yeah. For everyone here, I'm seeing it right now. It says that the answer is 0 for the third part. It also says there's no answer for the second part. Dude, this is so fucked. This is so scuffed. This is so scuffed. Yeah, so don't worry.
Did you work out part C then?
No, I will do it. Let me do all of it. Yeah, because I'm sure, Anch, you want me to go through this, right? Go through all this?
Yeah, after you're done with office hours, could you post all the stuff you went over this one?
Oh, yeah. Yeah, no, I'll post all this. Okay.
Thank you.
Anch, did you get how I got this for part A? We cool on this one?
Yeah, that makes sense.
Okay, breezy. All right, let's do part B. Yeah, dude. Oh man, this is so broken. Wow, you are doing great for children. Thank you, Fook Life. That's a funny username, Fook Life. All right, let's see. What is the potential what is the potential? Okay, this is cool. Okay. So potential is coming in from infinity, I think is what it is, right? Yeah. Ooh. Right, okay. Oh, interesting. Oh, wait. Oh, because it's plus Q and minus Q, right?
Yeah.
Yeah. So what's the electric field out here?
Well, it says the distance at R equals 2.5x, so
Sure,
that'd be halfway
sure.
through that.
Right. But when we calculate potential, right? We come in from infinity, yeah?
Yeah.
And we're going to do, was it delta V is equal to negative integral of E dot dl, right? So as I come in from infinity to here, there's no electric field here. So I don't even have to worry about this. You see that? There's no electric field.
Okay. Oh, okay. So your electric. Oh, okay. So it's constant. Wherever your
Yeah, it's
potential
constant
is.
and it's 0. There is 0 potential getting to R equals 3. We are going to go through some electric field to get to 2.5, but getting to 3, this is 0. Right?
So wait, outside the sphere, the big sphere, the electric
Mhm.
field equals 0 because the positive charge and the negative charge cancel
Yes.
out.
Yes, there is 0
Okay.
charge enclosed.
And if it's 0, that means the change in electric potential is 0. So anything starting from, I guess, so the value at the inside of the sphere, like between the mantle of the inner and outer crust,
Mm-hmm.
going to infinity, that's unchanged.
Yes.
Okay, that makes sense.
Okay. Okay, so now I need to go from one second. Yes, so I want to figure out what the electric field is going from here to now 2.5a. Okay.
Okay.
All right. Let me think. All right. So by Gauss's law, E times 4 pi r squared is going to equal this one. So this is Q, positive Q over epsilon naught. And then now I need the electric field here, not as a function of just 2.5, but still as a function of R. Right?
Mm-hmm.
Okay. Bum. Let's see. Does this simplify to anything nice? I think it has to eventually. Yeah, let me just slog through the algebra. Okay. This is what we had so far. We had... One sec. Yeah, okay. That was this. Actually, no. That was okay, I'll just replace the 2.5s with R's. Okay. So it's that, and then it's minus this. But now this is R cubed, and this is R cubed. Okay, but this is 3 cubed minus 2 cubed. This is still 2 cubed. And then, one second, let me think. Yeah, that's okay. I don't think I have any more A's in there. Wait a minute. Q enclosed, and then R Q. Oh, no. This is going to be... This will be A cubed, but then this will also be A cubed. Where is the A eventually going to come into play? Oh, when I do the integral, I think. No. Electric field's a function of A. One sec. Related rates, that is true. One sec. I have this kind of off. Okay. E 4 pi r squared, Q enclosed over epsilon naught, minus the amount of enclosed charge here, which is Q. And then I'm going to say 4/3 pi R cubed minus 2.5A cubed. No. R cubed minus 2A cubed. Oh, that's where the A cube comes in. Okay, here it is. Got it. And then this is over 4/3 pi. And then this is 3a cubed. 3a all cubed minus 2a cubed. There we go. Okay. All right. I was wondering. I'm like, where's that? I still need an a in it somewhere. Okay. This is 27 minus 8, so that's 19. Sorry, this goes away. So this is 9a cubed. Okay. And then this is now 8a cubed. So it's q over epsilon naught minus q. And then we're going to say r cubed over 9a cubed minus 8/9. Yeah. Why do they have 27 over 19? Oh, I see, because they keep the 4/3 in there. That's okay. Okay. Let me make sure this is right. 27 over 19? What did I do wrong here? Oh, there's another 4 pi in there, I think. Huh. Or... eventually I want to get to this for E. No, not that. That's eventually what I want to get to. I want to know where, like, 19 is coming to play, though. What do you think? Q. R cubed minus... was this right? 2a? Yeah, 2a and 3a. So that's 8a cubed. Oh. Oh, I know. I'm so sad at myself, dude. Jesus. 28 minus 8 is not 9. Or sorry, 27 minus 8 is not 9. It's 19. Yes. Okay. 27 minus 8 is 19. There we go. I was like, I need a 19. Where the hell is this 19 coming from? That's what I wanted. Okay. I'm feeling slightly better about this. And this is E times 4 pi r squared. And then this is still over epsilon naught as well. This is for E and M. Okay, so now I divide by 1 over 4 pi. And I divide over r squared. I see. I think I see. They want to combine this term and this term. Okay. Is that going to be a common denominator? Yes, it will actually. Okay, here's what you do. I see how this works. I'm going to multiply this by 19 over 19. So then I get 19q over epsilon naught minus minus. So that's plus. So this is 27 over 19q 4 pi epsilon naught over r squared. So that's where these all things combine to do this. And then this is going to be minus 1 over 4 pi epsilon naught. And then you have r squared on the bottom, but r cubed on the top. So that's going to be qr. Good. And then that's over 19a cubed. And then 1 over 4 pi epsilon naught is the same thing as k. This is k. So then I get that E is equal to KQ over R squared times 27 over 19 minus KQR over 19A cubed. Good. All right, there we go. I can do algebra. So I want to make sure I never take this. It's first year physics, Pinhead. It's not that crazy of a class. Okay. All right. We got the electric field, yeah? Good so far? I agree. There's a lot of like algebra
I
trickery.
That.
Well,
What I did was,
yeah.
I mean, do you want me to tell you what I did?
Well, we got to the electric field, so we haven't done the potential
Well,
yet. So
it's
tell me,
okay.
what'd you get to the electric field? Or did you not do the electric field?
I didn't do the electric field at all. What I did was,
How'd you get
voltage
potential?
total, or sorry, not voltage total. Electric potential total equals the electric potential of our little guy at the center, the point charge,
Yes.
plus the partial electric potential of whatever Q we were covering, right?
Okay.
And so I already, off the side, I already was determined what the point charge was. So I had the electric potential for that figured out. So then what I did was I did the integral of the change in electric potential from infinity to 2.a with the electric field times dr. I said the electric field was constant, and then I just had dr left. Then I kept integrating till I got k times the charge enclosed k times the charge enclosed over r, with r being subject between the integral bounds of.
Oh, so you're integrating. You were integrating voltage. Is what you're doing. That's what it sounds like.
Well, but what I did was I set because I thought the I made the electric potential on the outside 0. So what I was doing was it was just from the voltage was from 0 to whatever. Because by setting one of my bounds to infinity, I had k times the charge enclosed times 1 over 2.5a minus 1 over infinity. So 1 over infinity just went to 0. So I was like, oh, sweet. So that, I guess you could say my electric potential final was really just at 8.99 times 10 to the 9. That's my K. Times my total charge of the point charge A minus the charge of the enclosed, like, I guess, negative Q over just R. Or not R, but 2.5 times A.
Yeah, sure.
And that got me 3.84 times 10 to the 10 volts, where I messed up. I think my answer is wrong, mainly because whatever answer I got in part A for the charge of the partially enclosed negative Q, I just carried over into part B, and because that one was wrong, this one's also wrong. So my one calculus mistake at the beginning really shot me in the face.
For sure. I'm curious. So you treated this as a point charge to find potential. Totally valid. I'm curious if you can treat the partial thing as a point charge to find potential as well.
If I'm just acting like the like I'm only halfway through the outer sphere, I just was like, let's pretend the rest of it doesn't exist. We're just gonna do a Gaussian
that is the issue. Oh, that is the issue, though, right? Yeah, the issue is that, that's why you can't simplify it. Yeah, if you're looking right here, so this is contributing potential, but also this is contributing potential, and you just ignored this. You just said, I don't care about it.
Well, wasn't it only asking for the potential at 2.5a?
Yes, it is asking for the potential there, right? But the potential there, if you're going to do it with your method of saying like, oh, well, what's the KQ over R's of a bunch of the things that are around it, you have to also include this stuff on the right.
Wait, why?
Because it contributes potential. Because these things are like point charges as well. So, for instance, if you're trying to figure out the potential here, right? And then this is like a charge of plus Q. and it's located whatever a distance r here, right?
Yeah.
Because I can estimate the electric field of this as the same thing as just this, that means I can calculate the potential here as the same thing as being due to just a point charge, and that's just going to be kq over r. Because this and this produce the same electric field.
Yes.
Okay. The issue is that if we're doing this, okay, if we're looking outside of this, yes, I can reduce this to a point charge of minus q. That's totally okay if I'm looking outside. But you're looking inside the shell. And so this reduction of calling like whatever this proportion just a single point charge doesn't work, because you also have to consider the electric field being due to this stuff.
So
Like-
since I'm looking,
Yeah.
If I'm at that point 2.5a, which is
Yes.
inside the sphere,
Yes.
even if I treat the point charge, even if I treat that other sphere inside the bigger sphere as just a point charge, which
That's
I
totally
can,
cool. You can totally call that. That's totally cool
And-
because you're outside that one.
then I'm finding the potential between that point and my point 2.5a away.
Well, no. You're not finding the potential between these 2 points. You're finding the potential between this and infinity, technically. That's what delta V is. But if it was just a point charge, then coming from infinity to here is the same thing. This is a little hack. That potential is just equal to kq over r. That's for simple
Yeah.
point charges. Yeah.
That's
If-
simple. Okay.
Yes. So if or cases where you're outside the shape and it's spherically symmetric. When you're inside the shape, the electric field here is not the same thing as a point charge of just this amount of charge. Right? We showed that earlier in part A. Right? The electric field here, I mean, yes, it is kq over r squared for the center thing, but then look at this like mess that it is for partially through. Do you see how this looks nothing like just a single point charge?
Yeah, why does it look like that? It's what the
It's because the electric field is built because you're enclosing more charge as you expand through the thing, but you're also accumulating more area from Gauss's law. And so they kind of like fight each other. So in the whole like mantra of Gauss's law, right? You have E dot dA is equal to Q enclosed over epsilon naught. If something is solid, okay, let's say like solid and insulating, okay?
okay.
As you move outwards, right? So as my Gaussian surface starts expanding out from the center, right?
Mm-hmm.
My Q enclosed, let's say it's uniform. That's going to go as rho times 4/3 pi r cubed, okay? So do you see as r grows, the charge enclosed grows as a factor of the cube of that?
Yeah. Okay. Grows at a factor of r or
R cubed.
R to the cube. Yeah.
R to the third. But your E dot dA grows as 4 pi r squared. So now you have like, oh, rho 4/3 pi r cubed versus 4 pi r squared. So now E is going to be proportional to R. So what we're saying is like the E field grows as a factor of R. And this violates what we understand for point charges. Point charges have that E is proportional to 1 over R squared, right? For a point charge. That's the whole is E is equal to KQ over R squared. And so that's why something that's solid behaves differently than something that is a point charge, because the electric field grows with R for something that's solid and insulating, versus the electric field going down as a function of r squared for something that's a point charge.
Okay. Let me think.
Yeah, think about it for a second.
So, okay, so I see you have the electric field times the dA equals charge enclosed over the permittivity. This is a sphere, so your dA looks correct. Where does your permittivity or...
Oh, sorry, I
P-
lost my permittivity. Sorry, yeah, whatever.
Yeah.
It's supposed to be an epsilon over there.
Okay, so if your charge enclosed is your... are we assuming this one is
Uniform.
non-uniform?
No, it's uniform because it's rho. Rho is just a constant.
Wait, so how does charge enclosed equals... Wait, how does charge enclosed equal that?
It's okay. So charge enclosed, this is equal to charge density times the volume.
Okay. And your charge
Right.
density is constant.
The charge density is technically the total charge divided by 4/3 pi big R cubed. Like if I were to say like this is big R cubed. And that's why Q enclosed will look like the traditional thing we had. Do you see how it's going to be sorry, this is 4/3 pi R cubed. So this is going to end up equaling Q, and then it's 4/3 pi little r cubed over 4/3 pi big R cubed.
Okay, your 4/3 and pi cancel.
Right. Do you see how this is like part of the volume over the total volume?
Yes, okay, I see that now.
Yeah.
Okay,
So-
so that's how it makes your total enclosed charge.
Mm-hmm.
Okay. Then why did you just have the charge density times the volume? Why did you not simplify it down?
Because I wanted to show how each one of these sides varies with little r. This is a constant, right? The total volume of the thing is a constant.
Yeah.
I just wanted to show how the electric field changes as a function of where you are in the shape. So only as a function of little r. That's why I got lazy and I said, okay, I'm just gonna throw rho in there, and rho is technically Q over 4/3 pi r cubed, but these are all constants with relation to like where you are in the charge.
Okay, so those are all constants. And okay, so E, obviously if you rearrange your equation, you put dA under your charge enclosed with its permittivity.
Yep.
You basically set up so where E is proportional to R.
Good.
Okay. Then that's in the case. Okay, so this is in the case when you have a conducting sphere.
Non-conducting sphere.
A non-conducting sphere, sorry. So
Conducting
this is when
sphere,
you have
there's no
sphere,
charge enclosed. Yeah.
But down there, you're talking about when you have a point charge when E equals KQ over R squared.
Mm-hmm.
Okay. So when you go with a point charge, as you get closer and closer and closer, your electric field gets stronger.
Yeah. And
Or it
the
gets-
main thing
It gets
the main thing
stronger at
here
a
is
much
that
faster rate.
when we know that things behave like point charges, we can just say that the potential is KQ over R.
Okay. So
This
that's
is
why, okay.
this is the easy hack. But I wanted to show you that when you're partially through something that's solid and insulating, you can no longer call it a point charge because the electric field no longer behaves like a point charge, and so you can't do this KQ over R.
Okay, so whenever I was calculating the okay, so whenever I was trying to calculate the electric potential of my, I guess the partial Q,
The minus
that
Q,
weird-
yeah.
the minus Q, yeah. My partial minus Q, I was treating it like a point charge, and that's why it was wrong. Okay, that makes
Correct.
sense.
Yes.
Okay, that makes. Well, I think I reasoned out to like, okay, if we're pretending like as I'm going from infinity to 2.5,
Mm-hmm.
if we're okay, if I was just pretending like the 2.5 to 3a just didn't exist, which is
Correct. Which you would be
That's-
correct. So no, if you're outside, which technically if you said it didn't exist, then you can treat it as a point charge. So
Yeah.
let's just say, for instance, you're looking outside of your solid thing, right? And there's nothing else around it. Now, Q enclosed is staying constant again. So out here, Q enclosed is constant. So when you do E times 4 pi r squared is equal to Q enclosed over epsilon naught, now when you move that over, you get that E behaves as 1 over r squared.
Okay. Is the red where it's completely outside
Yes.
the large sphere? Okay.
Yeah, this is
So when I'm outside of it, and if I
Outs-
treat it like so when I did treat 2.5a to 3 as if it didn't exist, my math
Yeah.
was right, but it still exists.
Yeah,
That's
2.5 to
why
3
I
still
sh-
exists. Correct.
I shouldn't have treated like it didn't exist.
Yes.
Is that what you're saying?
Yes.
Okay, then. All right. Yeah. No, I was okay. Yeah, this was
No,
definitely.
you have a good way of thinking about it, because it is very useful sometimes in E&M to reduce things to point charges. We do it for like the potential of the infinite like ring. We do it for the infinite line, whatever. The issue is that the application of it, you have to be careful about when you can use that trick.
Okay, so I couldn't use it for this trick because obviously that. Well, the mass, or not, I guess the total volume I was worried about, I was kind of just discounting then, right? Because infinity to 2.5a, the only real volume that has charge is 2.5a to 3. And by treating it as if that didn't exist, I was, one, throwing out charge I should have been tracking, but two, when I was reducing, okay. So I was still counting the partial charge of 2.5a to 2a based on what I did up on the first problem, even though the total charge I got was wrong, because I made a calculus mistake and that just kind of snowballed. Okay, so I see why that's wrong. But does my method of like doing the total electric potential equals the point charge plus, I guess, like all, I mean, I guess, yeah, if I didn't say just like the partial, actually, hold on, in this question,
Yeah.
I should have just, hold on, let me think. So for part B, when I was setting up my equation, the total electric potential equals the total potential of the point charge in the center, or at least I set it to a point charge, plus the electric potential of negative Q.
Yeah.
Was I correct to assume I just want to take the, I just wanted to grab the stuff from 2.5a to 3, right?
Well,
Or not
so
3, but no.
So when finding the potential, there's two ways to do it. If you're just dealing with point charges, then yes, you can say KQ over R, KQ over R, great. When you're not dealing with point charges, or you're dealing with potentials of like weird like locations and things, you need to figure out the electric field first. And then you need to integrate the electric field from infinity to your position.
Okay, I see.
So that's why in part A, we had you to determine the electric field at 2.5a. And then from the electric field, if you have an equation as a function of R, now you can integrate that to figure out the potential. I was trying to like guide like steps. Like in order to get potential, you need electric field first. So that's why we asked for electric field first.
In A to use in part B, yeah.
Yes, that's usually why things are scaffolded.
Okay. Well, give me a moment.
You're good.
So my approach in part B should have been, instead of trying to find the total electric potential of just, I guess, the point charge plus the electric potential of my 2 to 2.5a of that negative Q charge, I should have instead gone with what's the electric field at this point.
Yes.
And then I should have worked, I should have worked from there.
You need the electric field as a function of R, not just at 2.5a. You need it as a function of R.
Yeah. Should I have set the bounds? I should have set the bounds. Okay, so I should have, if I did the work correctly in part A, based on what using what you did as an example, then what I should have done is I should have changed my bounds from 0 to 2.5a to just infinity to 2.5a. Now going from outside in. Right?
Yes. Well, no. You want to go from 3 to 2.5 because the electric field is 0 outside of 3. Because outside of 3, yeah, this equation that we came up with for the electric field only works for between 2a and between 3a. The second you get outside of 3a, now the electric field needs to go to 0.
Okay.
Which I think
then,
maybe it does actually, right? Because what would that be? I need.
Well, it ends at there would be something like one. If there's a constant over infinity, it'll just go to 0 based on similar to what I did in mine.
Yeah.
Because I think it was where was that? There was like one part in like part. I don't know. There was like a hint like, ooh, you should go to infinity on this problem, but it might not have been on this one.
Yeah.
Like I distinctly remember there was like a little note. Hey, maybe integrate to infinity. Wink, wink, nudge, nudge.
Nudge, nudge. Wink, wink.
Yeah.
Yeah.
Okay. Maybe I'm hallucinating it, but I remember that. So okay. So I should have done that approach, and I should have just ran with the electric field I had at that point. Not at that point, but the work I did in part A, I should have used in part B.
Correct.
And then I should have changed the equation so I could modify it from infinity to 2.5a.
No, you just wanted to go from 3 to 2.5a. Because
Okay,
the equation you
3.
came up with in part A is only valid between 2a and 3a.
Okay, then okay.
The reason why you don't need to deal with anything outside of 3a is that the electric field is 0 out there.
All right, yeah, that makes sense. Then okay. Then can you go over part C? I think I need to look over this one more when I'm studying.
Sure. Well, so you would take this, and then you would need to integrate this from 3a to 2.5a. E.dr. And so then this would end up becoming negative kq over r, 27 over 19, evaluated from 3a to 2.5a. And sorry, that's a minus, so that's a plus. And then this would also become, I think, a minus. No. This would become plus, and then this would be kq r squared over 2, 19a cubed. And then again from 3a to 2.5a. And then you need to solve this. Which, yeah, it's kind of a pain. Algebraically. I think so. I'm missing 27 over 19. Yeah. Right. 1 over 3. Yep, okay. And then, ooh, this one should have been minus, maybe? No, they have the minus in the other place. Yeah, okay, we're fine. I think. Yeah. Okay. Yeah. Then you solve for this, and then that's your potential. Okay. Part C, you actually part C was actually quite easy because you don't actually consider anything about the fucking shell and all the other stuff. Okay. Right, okay. So, for part C, let me pull the image in. Okay. Part C, they ask you to figure out the capacitance, or no, wait. Just find the capacitance, and then I gave you a hint. Okay. So this was, now assume that both the inner sphere and the outer spherical shell are conductors. So they're no longer insulators, okay? What is the capacitance's configuration? So now I want to figure out what is the potential, because remember that capacitance is equal to Q over delta V, right? And so I want to find delta V from here to here. So delta V in this case would be from, I don't really think it matters which direction. You'll just make capacitance positive at the end of the day. But the potential is going to be greater for the 2A. Okay. So it's going to be potential at 2A minus the potential at 3A. Okay. Now, when I'm out here, right, I'm not touching this conductor. I'm not in this conductor. So I actually don't care about this conductor when calculating potential. So I just need to figure out from here to here. So I want to do, so delta V is going to be equal to negative integral from R is equal to 3A. Sorry, from R is equal to 2A to A of E dot dl, right? And what's the electric field in between 2A and A? Well, that's the same, because we're outside of this thing, that's just a point charge. So for R is in between A and 2A, E is just equal to K positive Q over R squared. Does that make sense?
Yeah, so far.
Okay. So now I'm just going to do, okay, so negative 2A to A, KQ over R squared dr. This is going to get me my standard equation for potential. So I'm just going to get KQ over R evaluated from 2A to A. And so that's going to be KQ over A minus KQ over 2A, which is equal to KQ over 2A. And so then capacitance is equal to Q over V. So that's Q over KQ over 2A. Cancel, cancel. And I just get 2A over K. There you go.
Okay, 2A over K.
Oh, and sorry, no more V in it. I don't know why I put a V in there. Sorry.
Okay. Admittedly, I mean, I think I told you this. For part C, I just stuck an equation off my
Your equation sheet, which is totally valid. It's valid.
So what I got was capacitance of a spherical capacitor with a vacuum equals 4 pi permittivity of free space times radius 1 times radius 2 over radius 2 minus radius 1.
Okay.
So what value, let's see, hold on. You got 2A. A was in this instance 0.301. 2, that's over K, 8.99 times 10 to the 9. So, yeah, you got negative, okay, so wait, I did get that one correct. 6.69 times 10 to the negative 11. Okay. So right now on Kudu, it is telling us that it's 0, and that is wrong.
Yes, it's totally wrong.
Okay. All right. Yeah. I guess. Okay. I see. Yeah. Okay.
Cool.
Thank
Ansh,
you
is
very
that?
much. That helps.
You're very welcome, Jack. Ansh, does that answer your questions about this stuff too?
Yeah, that was really helpful. Thank you so much for all of the explanations.
Oh, you guys are totally welcome. Cool. All right, I'm gonna download all these things as a PDF, and I'll put them on
if you
Campus Wire for
could
you
do this
guys.
on Campus Wire, I'd love that.
Yeah, I got you guys. Also, these recordings are always on there.
Okay.
If you ever go to the YouTube, and you got to go to live, I think is what it is. Yeah, my channel. Go to live, and then it'll be here. All the recordings are in here. Okay, cool.
Do you have a few more minutes for us to ask questions?
Yeah, what's up?
Okay. Let me see. On one of the questions for like they have to give some mathematical answer. I did everything correct except I made one small math error and put a 7 instead of a 1 on one of my things.
That's fine.
How many points would I lose for that?
It's
my
like
answer.
0 points, maybe like half a point.
Okay, because it was the end solution was 0.13 off
Yeah.
from what it should.
Again, on the regrade request, if you just like highlight being like, yo, like I made a transcription error from like a 7 to a 1, that's okay. Just point it out to me and see that like, oh, it would have been the same. And then, yeah, I'll give you credit for it.
All right. Yeah, that's okay. That's a big help. All right. Based on like what I told you for parts A and B for like questions 10.
How many points do I get, dog?
How do you think I think
It's always the questions. How many
where I
points
made
do
a
I get?
mathematical mistake in part A, it definitely carries over into part B. But I think I did part B so wrong that I didn't do it very well. So
I'll always give you guys at least half credit. At least half credit. I'll try to like give as many points as I can for like right methods and per se. I mean, and it helps that we went over it in office hours. I pretty much know what you did at this point. I'm still gonna make you like write a regrade request about it. You still gotta like document it just for your own sake, so you remember not to do it again. But yeah, it'll be more than half credit if that helps.
okay, thank you. Yeah. Then I have 2 questions from homework 9.
Okay. Maybe can we do this tomorrow? Maybe because it's kind of late.
Yeah, hold on. Let me.
Just because we've been going for 2.5 hours now. I'm getting tired.
I mean, it's like one question. It's real quick.
Okay, is it real quick?
Yeah,
All right,
it's just
what is
on
it?
question 8, for part homework 9.
Okay.
It's basically asking you to find the charge density from basically between 2 metal spheres with like different radii separated by a large distance. And I integrate correctly, or not integrate.
Oh,
but,
this one?
Yeah, I get this
Yeah.
one correct, except for one thing. I originally had it as 1 over r2 r squared minus 1 over d minus r squared.
Mm-hmm.
I don't know where they get that extra r and r minus d, or
Yeah, it has to do with magnitude and vectors. So current density, I think, is technically a vector.
yeah, it is.
So if it's a vector, you need like r hat times r. Oh fuck, what is it? Yeah.
I think it's
The-
r hat is equal to the r vector over r.
Right, so r times r hat is the vector, right? That's why you multiply, I think, by another one.
So I should have done a matrix, or I should have done like
Not a matrix, but you got to make sure you. Again, I'll go over that one another time because it is finicky. That one is a little finicky. I have to like show kind of arrows and things and how like vectors work.
Okay, got it.
Don't worry, I'll do it another time. Yeah, that's
Alright, then those are all my
if you want to
questions.
take a look at it, yeah, that's what it is.
Got it. Thank you very much,
Okay.
then.
You're good. Anj, what's up? You got any last minute things?
No, not really. Should we do? I mean, will there be an announcement soon about regrade requests and stuff?
Yes. Well, once like
Okay.
Kudu gets back to me about like why the fuck 9 and 10 are duplicating. And...
So we should only email like after that.
Sorry.
Details about- We should only email for like after like it's graded and stuff, like for details
Yes.
of our work.
Yeah.
Okay,
Yes.
sure.
Yeah. Don't worry about anything right now. Yeah. Wait. Please hold. I know it sucks. I don't want to hold. I want to like go right into the final, but I have to wait for them to fix it because like, bro, it's such a fucking mess, dude. It's a disaster.
Well, thank you so much for your time.
You're welcome, on. Come on by tomorrow. I'll be here as well. Callisto. Bye. You're good. Callisto, would you have time for one more question? Oh man, I'm so exhausted. I'm so tired. Let me see. Hecker, are you still Hecker? I feel bad. Hecker was asking me the other day. He's like, man, Dr. Gold, I feel like you never have office hours anymore. And I'm like, I do. It's just a lot of UCLA these days, which is okay. It's at the beginning, there's like nobody. Then towards like the end of the year, everyone wants help, which I love it. It's great. I'm glad that people are asking for help. But I feel bad I haven't been able to get to any of these. Yeah, these are cool. These are great questions. This is also a great question. Yeah, Fembox. No, dude. That's what it is. That's what you deal with. These students are actually pretty good. They're not that bad. When I teach pre-meds, oh my god.
You done messed up, Aaron!
No.
That's the absolute worst, dude. Every other question from the pre-med students is always, is this going to be on the exam? How many points do I get? What about this? What about this? What about this? You know, these students are like way chiller than like the pre-meds I teach sometimes. This is why I can no longer be a teacher. You do have to have patience. Yeah, you do have to be very patient. No, you're fine, Fembox, dude. Dude, your comments out of line. Where's Sensation?
Yeah.
Sensation or Jeff.
My name is Jeff.
Jeff, I guess Jeff isn't as out of line, but Sensation, dude. I love Sensation's comments sometimes. Just absolutely like hilarious. Jeff is here. I called him, dude. It's his mating call. You know what? Yeah. Pinhead for this one. This is something with periodic solutions. Oh man. I don't know how to do this off the top of my head. I probably could find it out. What I'll do here, I'm just gonna dump everything that's in the queue right now. I'm gonna put it into. I've taken a vow of silence. Yeah. Yeah, I'm gonna post it in my Discord. And Pinhead, if you're part of my Discord, I'm sure someone will do it to help you out. Otherwise, I can do it probably tomorrow. If there isn't someone else asking a UCLA question, if you get here like right on time. The UCLA students don't usually show up for like first like 20-30 minutes. So yeah, let me do that. Here, let me just post all. I'm just gonna clear the queue real quick of everything. Go drink some water. Noise, baby. What's up, Noise? Oh man, I've missed my boy, dude. What's up, Noise? I've missed the lads. Dude. Hope you're doing well, Noise. Henlo, as we say, dude. I'm just finishing up. We were streaming for almost 2.5 hours. I had a lot of UCLA students. I'm teaching a summer course, Noise, at UCLA this summer. I'm teaching Physics 1B. It's like the second quarter of like first year physics. It's for engineers, so like there's a decent amount of calculus in it. We got some integrals and stuff. And so yeah, they were asking some stuff today about like circuits. I feel like aren't you doing like electrical engineering? I feel like you had some cool. Noise is an OG. Noise has been around for a while. Noise is before your time, Breasticles, actually. But Noise is over in the UK, and I believe is in an engineering program for uni or college or something. I do enjoy it. Noise. Noise, baby. I gotta make another trip to the UK and actually come up to the north part, like Lancaster and stuff, so I can come see you guys. Yeah, there you go, Lancaster. Nice. I'm so glad you went back to uni. Congrats on finishing your first year, dude. That's hella fucking dope.
That's dope.
Good stuff, Noise. Noise. Yes, dude. I feel like Breasticles and Noise would get along very well. Y'all are both kind of like similar, just like kind of math, physics chads. Noise told me the glory that is Weatherspoons, which has like, I think it's like 2 quid pints or something, dude.
Yeah.
Stuff is so cheap. Top marks, good job, dude. See, I knew things would sort out for you. I knew you'd figure it out. Everyone figures it out eventually. I say that. Everyone in life figures it out. That or they go to jail. And you're not going to jail, so good. Great. Dun, 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 dun. 1.99 for a pint of Worthington's Cream Flow. There you go. That's what I'm talking about, dude. 2 quid for a beer, dude. Man. I was spending 10 over the weekend, dude. It was $10 for like a, I don't know, like a basic Modelo. It's ridiculous. $10. Yeah. Okay. I need to head out. Let's close out the stream.
My name is Jeff.
All right. Thank you everyone for coming to Actual Education Office Hours today. Appreciate you, Noise, coming back to say hi. Welcome back and everything. Come say hi in the Discord. We'll be streaming the rest of this week. This is my last week teaching at UCLA for the summer. So I promise after this week we'll have a more like interactive. I'll go back to streaming on Discord and stuff. But if you're ever wondering about the calendar when we stream, this is the schedule. Come on by, ask your math and science stuff. We'll be doing more. This Friday is their final exam. So after this day, all of these days will be a lot more open for me to kind of just shoot the shit and just do the fun stuff we were doing on the Discord all the time. We'll probably have a chess tournament actually on Friday. I'm going to see if I can do this. So look out in the Discord. I'll make some announcements for things. Final exam. Yes, they have their final on Friday. So expect there to be a lot of UCLA students showing up to office hours in the next couple days. But after Thursday, we're done. Totally done. It's been a crazy 6 weeks teaching these students. Just it's so nonstop. They wanted me to do a second set of this. They're like, do you want to do session C as well? Which would be, I would get like a week break and then another 6 weeks of this.
Oh no.
Absolutely not. Absolutely not. You gotta give them that video to study, dude. I have it saved. I love this video. Noise, I feel like you would love this. It's a quality meme.
Honesty has always been our policy.
1 sec. Here, I'll dump the link. I'll dump the link for you. Rascals showed me this. It's absolutely just fucking comedy. They said just watch this on repeat.
希伯来语里亚当这个词的意思，人是神照着自己的样式创造的，在神的世界里，人的存在是有目的
Just
和
increase your
作用
brain power, dude.
人
Just
逃跑躲避神，当神找到
stare at this
人
and
他们开始推卸责任，互相指责对方是第一个叛逆人。
Mozart left ear, Bible Chinese right ear, audio visual enhanced learning experience. I still crack up at this Breskos. This is absolutely comedy, dude. I can't believe it's 2 years old. I've never seen this. Okay, let's go raid someone. Let's go say hi to another person on Twitch. I went to a Twitch meetup actually over the weekend on Saturday. It was like a beach party for a bunch of Twitch streamers in LA. I met some really cool people. A lot of cool like IRL streamers. I met some chick who had like 70k followers. Just nuts. Some of these people. Wait, first. Look up Dino Blade. Okay, I'll look up Dino Blade for you real quick. Dino Blade. Dinosaurs with swords. Oh man, dude. Let's see.
Doing an attack and disappearing.
So wait, it's
Now,
dinosaurs
on
holding
the defensive
swords in their
side of the most
mouth.
common move is going to be parrying them.
It's freaking badass, he
Slayer
says.
Kimetsu no Yabe. Just about every attack with incredible flourishes, and staggering a foe for long enough even results in a
I don't know, this just reminds me of, did you ever see those terrible movies like Sharknado? There's Sharknado 5, dude. Excuse me. Yeah, they're just like, yo, just put more sharks in it, or put more like dinosaurs in it. They were like, oh yeah, Tara Reid was in these, dude. Oh my god. The other one was like Mega Shark versus I don't know, dude. Some of these movies, Mega Shark versus Mecha Shark, or Mega Shark movie. Yeah, more great stuff. There it is. Mega Shark versus Giant Octopus. It's another one. That's kind of what that game just reminds me of. Just like, yo, you know what would be cool? Like a fighter game. Would it be even cooler if the fighters were dinosaurs? All right, let's go say hi to someone. Not many people streaming actually right now today. I think a lot of people take the summer off. I'm a big person. I'm a big fan of consistency, though. Still gotta stream. Okay, cool. Let's go say hi to Shark Geek. Looks like they got 108 people on their fundraising for Twitch's first live shark encounter. We can talk about Mega Shark. Don't you dare talk crap about Sharknado. Thank you, Pinhead. Thanks for the donation. Sharknado what? Sharknado 1, 2, 3, 4, or 5? Appreciate it. Okay, let's go say hi to Sharknado, dude. Shark Geek. Enjoy the rest of your money. Thanks again, Pinhead, for the donation. Appreciate you, man. We'll see you tomorrow. Peace.
That's a big tiger. I think she gets even closer in another pass later. But this was kind of a common theme where she would like pass by and then disappear for a while, and then we'd see her get it. Yo, Actual Education, what's up? Thank you so much for the raid. How are you doing? I'm gonna rewind a little bit so you guys can see that tiger shark clip right there. But thank you so much for the raid. What are you working on today? Guys, Actual Education is, as the name implies, an actual educator. Another fantastic person we had the chance to meet at TwitchCon. How you doing, brother? We were just talking about cinematic masterpiece, which is Shark.